the formation constant of a complex ion. In this case, our complex ion is the ammoniated silver. So we've got silver ions in solution. We've got, this is the overall reaction. Solution. They form this complex ion. Let's see. Yeah, that's right. And two of those plus. Okay, and what we're after is the formation constant for that reaction. If we just write out the formation constant, what's required, then we get the complex ion divided by silver and ammonia squared. The problem with trying to determine this experimentally is everything's in solution. So it's hard to get at if we want to do it titrometrically, which is the way we're going to do it, we need some way, a color change or a precipitate, which is our chosen method. So we need to have another reaction going on at the same time that allows us to detect the inflection point when we have an equal amount of, when we have the equilibrium situation here. So the reaction that we've chosen is silver and chlorine. All right, so we know that the solubility, we know of the solubility product for silver chloride, which is a solid, and it gives us this. So we're going to have a K, okay, KSP for this one. And we know what that value is. Let's see, 1.6, no, 1.7 times 10 to the minus 10. 0.7 times 10 to the minus 10. That's on the second page. Okay, so if we've got both of these reactions going on at the same time, then we can combine them into a single reaction. Okay, that will cancel out this term and leave us with this reaction. And the chloride ions. Okay. So if we do that, then our new KEQ here is equal to KF times KSP. Okay, the KEQ expression then is going to be the complex ion times the chloride ion concentration over just the ammonia. There we go. Okay. I think, and this doesn't have the KSP term in it, and we want to get that term in here. So in order to do that, we need to reincorporate silver. I believe that's the way we do it. Yeah. If we look at this term here, what does that KSP mean? That means silver ions times chloride ions, right? So if we solve that one, if we solve this one for the chloride ions, right, then we get KSP divided by silver. Okay. You just leave this on that side and bring this over here to the denominator. That means we can substitute that value in for this one right here. And then we can put KSP over silver. And then ammonia down here. But we know if we put it like this, then and if we bring it into the denominator, then this flips. So that leaves silver on top and KSP on the bottom. No, that's not right. Is that right? Yeah. It should be right. No. We solved it the other way. Now, why is it that? Silver. Oh, I see. Okay, sorry. Let's do it this way. Put the chloride here. Then we can go to the expression for formation constant. And we can take that one. Yeah, we can take that one. That leaves this in the numerator. And then we can substitute KSP here. All right, that gets us times ammonia. Yeah, and then all what we've done now is just the denominator of the denominator is the numerator. So that puts this one up here. All right, it's getting sloppier as I go. And that leaves KSP down here and ammonia here. Okay. So in order to solve this equation and identify what that is, we've got this is known. We need to know the concentration at the point where we start to form the precipitate. When we go in this direction, form the precipitate. We need to know what's this concentration, what's that concentration, and yeah, what's this concentration? All right, that's the theoretical part. Then the practical application, let's see, which one of these am I going to keep so I can erase the right ones? Okay, we're going to take, if we take this expression and resubstitute for the KSP here, then we get, move it down just a little bit. Then we get this concentration. And this is a calculated value, depending on the point of formation of the precipitate. I'll show you how to do that in just a minute. We get that one there. And then we resubstitute what is KSP. Well, KSP is silver times chloride. So this is simply a practical approach to what we do with the numbers. Now that we have this expression equal to KF, then we can take that expression, and I'm gonna have to erase these. We can take this expression and work backwards. So what would the equation look like if we were to, if this equilibrium expression were derived from the equation, what would the equation look like? So these terms would be on the product side. These terms would be on the reactant side, correct? So we're going to do that. So we've got the silver, and then we've got the chloride. Oops, that's not right. Chloride ions. And we've got ammonia, 2 of them. Okay. And they're in equilibrium with the complex ion. And this chloride. Okay. So if we move to this little table, that's what we've set up. Oh. Yeah, y'all didn't say anything. There. I know you got the hard copy, but unfortunately that's being recorded even though we couldn't see it. Okay, so the way we set it up is with the ice table. We're going to use an ice table here. And I haven't talked about the procedure yet. Maybe I better do a little bit of background for the procedure. Yeah. That's enough theory for now. Let's look at the procedure. Okay, so let's look at the materials first. We're going to have a solution of known concentration of silver nitrate and known concentration of ammonia. Now that 1.000 is a nominal value. The label on the bottle will tell you the exact concentration, because I had to go do an acid-base titration and determine what it was. Because you can't depend on the ammonia concentration in a bottle of ammonium hydroxide and then dilute it to what you think is the right concentration, because it doesn't work that way. So I got close, and then I titrated it. So that value will have to be substituted in there. We can determine the exact concentration of potassium chloride. I've got a 0.140 molar potassium chloride. That's what we put in the burette to titrate with our complex ion. We need the volumetric flasks to, I'm not sure why I got 4 of them in there. You need a volumetric flask to prepare the complex ion solution, because you're going to put silver nitrate in there with ammonia of a designated amount, which is on the next page. Okay, right here. Oh, I know why. Because we're going to do triplicates. So we're going to use 5 milliliters of silver nitrate, and we're going to use 10 milliliters of the ammonia solution. and we're going to dilute it to exactly 100 milliliters. All right, so those have to be known quantities. Then we titrate it with potassium chloride until we get just the faint visible precipitate. It's very difficult to see. So we dim the lights and we use the Tyndall effect. Get a flashlight, shine it through your solution. And remember, precipitates are you're going to see the light beam in the solution. If it's a solution, remember the Tyndall effect, the light beam, you can't see it. You can see it going in, you can see it coming out, but you can't see it in the solution. So if we get a precipitate, then you can see the light beam. And that way it's easier to detect the endpoint. And that will be a certain volume of potassium chloride. We'll be able to calculate the chloride concentration before and after. And then we'll also have the volume, the total volume at the endpoint has to be known so that we can calculate the equilibrium concentrations of everything. Right? We know what our concentration is to start with, but we're going to add some solution to it, so the concentration is going to change. So that's the purpose for having all those known volumes. The total volume then will be used to do the further calculations, and we'll get to those in just a minute. Okay. So I'm not sure why I said 4 flasks. We only need 3 volumetric flasks. And we're not going to use Erlenmeyer flasks. That needs to be changed. We're going to use 100 mil, no, not 100, 200 milliliter. 200 milliliter beakers, because you got to be able to get your burette tip in there right next to the pH meter probe. And the Erlenmeyer flasks have too narrow a neck. You can't fit them in there together. So we'll use beakers and on a stir plate with a magnetic stir bar in it, so you don't have to remove it, swirl it, put it back on there, which is the way they made us do it when I was a student. Actually, the volumetric pipette, okay, 5 and 10. We only need a 10, I believe. Yeah, you only need a 10 milliliter volumetric, so that also needs to be changed. Oh, excuse me. No, I'm sorry. You do need both of them. 5 milliliters for the silver, 10 milliliters for the ammonia. So I gotta be sure you have those available. Okay. I thought I had it set up. I'm gonna have to pull in some more stuff. All right. Once we've got those known volumes and known concentrations, then we can calculate the initial conditions. Right? It's obvious initially we're not going to have any of this, we're not going to have any of that. Right? Initially we're going to have 0.5 millimoles of silver, and it's easier to do it this way in absolute amounts, so that you can once you've determined the equilibrium amounts, then you can determine the concentrations because you know the total volume. Okay, it's much simpler to do it this way. So with silver, if we're going to put how many, 5 milliliters of 1 molar, what was it? Yeah, 0.1 molar, 5 milliliters of 0.1 molar silver. So we got 0.1 molar silver chloride, so it's 0.1 molar silver. And then we're using 5 milliliters. So 5 times 0.1 is 0.5 millimoles. Milliliters times molar is millimoles. 0.5 millimoles, right? Okay. So I haven't given you this one yet, but when we form it, when we do the initial preparation, we're going to have to use a nominal value there, which was 1 molar? No, 10 molar, right? No. How much? 1 molar. Right, 1 molar ammonia. Yeah, it's going to be a little bit less than that, but we're going to use that for our calculation purposes. 1 molar times 10 mils. Right? So if we say this is 1 molar, oops, not there, over here. 1 molar and 10 milliliters, that's where we prepare it in our 100 milliliter volumetric flask. Then 10 times that is 10 millimoles, right? Millimoles of ammonia. Yeah, 10 millimoles. And in the beginning, initially, if we titrate it and we end up with a volume of chloride, potassium chloride, at 1 mil, if it only takes 1 mil of 0.1 molar, and it takes 1 mil to reach that endpoint, then, and this is before they react, right? We've put this much in, that much in, and now we're going to add this much, and we know at the point of equilibrium, when we form the precipitate, then we've got 0.1 millimoles. Okay, so what kind of change we're going to have? Well, obviously it's going that way. And what we've done is we've used up all of the silver, right? The change minus 0.5. So that's 0 at equilibrium here. And we've used up all this, right? Yeah, we've used up all this. So that's 0. So how much of this did we use up? Well, the ratio is 2 to 1. And if we used up 0.5 of that, then we needed 1 of this, correct? So that means we would have 9 left, millimoles here. Okay, so what did we get on this side? Well, for every 1 of these, we get 1 of those. So this is, excuse me, not 0, it's 5 millimoles of that. And we used up all the chloride, so it ends up over here. Right? Okay. So now we know at equilibrium we have these values. Oops. Got 5, 1, 0.1. And then all. Okay, so when we do our calculations, we have, okay, well, this over here, well, actually, this, the only reason I did this was to set up that equation so I could track the movement of our various components. For the calculation, all we need to know is the equilibrium concentration of here, right? No, our modified version. Where is it? Did I erase it? Oh, here it is. Before we did that, this is KF here. Substitute that. We calculate the ammonia concentration, put it in here. Chloride concentration, put it in here. And silver complex ion, put it in here. So how do we do the concentrations? Well, we know that we started with 100 milliliters. How many milliliters did we add? we added 1 milliliter, right? Okay. 1 milliliter. So the total volume is 101 milliliters. So we just need to divide each one of these by 101 milliliters because millimoles divided by milliliters is molarity. Divided by 101. And those values go into this expression right here. Bang, bang, bang. We know that one already. We get that. I know that's a complicated math, but it works. And then we want to compare the value we get with the accepted value, which is up here somewhere. There it is. 1.6 times 10 to the 7th. AF accepted. 1.6 times 10 to the 7th. That varies a little bit. It doesn't vary here, it varies here. Sometimes they say 1.5 and 1.7, depends on the author. We're going to use 1.6. Okay, I don't think there are any pre-lab or post-lab questions here. We're just going after that value. Yep, that's it. That appendix on the end, all I did there was, what I wanted to do was to show that in our ammonia solution, remember ammonium will not complex silver because it's not a base. It's not a Lewis base. It doesn't have any lone proton electrons. So I wanted to just show that at this concentration of ammonia, we have 99.6% of it in the ammonia form. So it's technically we probably should correct for the 99.6 value in here somewhere. Right, right here. Whatever that value is, multiply it by 0.996. But that's a little too much sugar for a dime, I think. Okay, any questions? Hopefully it'll make more sense once we get data to put in here.